Servomotor is a staple of Arduino projects. It is the first thing that comes to my mind when I think about making something with Arduino. Cheap and popular, excellent at their job. Do you want to make something move? 90% of time servos are the best option. So let's see how do they work, how to use them with Arduino, and do some testing. What I have here is a servomotor. The model is SG90 mini servomotor, the cheapest one that I found. They will be ideal for the first time using servos. Right out of the package, it surprised me how tiny they are.
That's normal size.
I mean, I should expect it, since they only weighed 9 grams. Operating voltage is 3.5 to 6 volts. Torque is 1.2 kilograms per centimeter at around 5 volts and 1.6 at 6 volts. Speed is 300 degrees per second and motion range is 180 degrees. So without any resistance, it should turn from 0 to 180 degrees in around half a second. Generally speaking, servos do two things: rotate in one direction or rotate in the opposite direction. We can see three cables going to the base. Red and brown are power cables and orange is a signal cable. Power can be supplied from Arduino, but with more servos and different components, it won't be enough. That's why for now, I will use Arduino as a power supply and later connect them to a different source. The signal that is supplied by Arduino is digital, and to control servos, pulse width modulation is used. I will talk about it more in a bit, but first, let's see what is inside this motor. At the top, we have a gear assembly. Gear ratios are chosen to lower rotation speed and increase torque. The electric motor connected to gears has a high speed, but a low torque, and to move some weight we need a higher torque. The DC motor is located in a lower part and connected to a driver board. Also, there is a potentiometer. Its knob is connected with output gear, and it is used to check at which position the arm of servomotor sits. The board takes a signal from Arduino, compares it with the potentiometer reading, and rotates the DC motor according to it. To understand more about how it is controlled, we need to talk about PWM signal. On Arduino we have three main types of pins: input-output digital pins, analog input pins, and power pins. Power pins are, well, for power. Analog in, to read analog data from, for example, sensors, and digital pins, which can receive and send digital data. Some digital pins have this tilde sign next to them, meaning that they can transmit impulses with a variable width. Through this, signal can be interpreted differently than just a 1 or a 0. We can divide signals into digital or analog. If we make a graph of how the voltage changes in the time, the analog signal takes the form of a smooth wave, while digital is a square wave, either high or low. Analog signals can transfer more information, representing any value in a range. Digital signals are either 0, so no voltage, or 1, meaning max voltage. Each one has its advantages and disadvantages. Analog can carry more information in less time, take less bandwidth, and can more accurately represent physical phenomena, such as sound, light, temperature, and position. On the other hand, they are prone to disturbance and distortion. Digital is less prone to interference, easier to process, generate, and store by computers and microcontrollers, but they require more bandwidth to send the same amount of data as analog and are less accurate due to their values being discrete. Arduino is only capable to send signal in a digital form, and to control some devices it uses variable pulse width, PWM, pulse width modulation. For example, if we connect an LED to Arduino, we can use either digital write or analog write to turn it on. Digital write sets the pin to either low, which is 0, or high, which is 5 volts. In this case, the LED turns on at a full brightness. Analog write isn't really analog, it uses PWM, and in case of an LED, it can be used to dim it. It turns the signal on and off in cycles, meaning that LED is constantly switched on and off. It happens so fast that we perceive it as emitting less light, It uses PWM duty cycle, percentage of signal which is high, in the set amount of time. Analog write with value of 255 means that signal fills 100% of a cycle and corresponds to 5 volts. 127, 50% of cycle and corresponds to 2.5 volts, and 0 means 0% and 0 volts. Servomotors use something similar, but instead of checking how much of a cycle is set to high, it uses the width of an impulse. We can see that in datasheet, a pulse is checked every 20 milliseconds, and the arm of a servo rotates depending on its width. 1 millisecond pulse means minus 90 degrees, 2 milliseconds means 90 degrees, and everything in between can be used to control 180 degrees of rotation. So, to control servomotors, do we need to make a code that uses PWM? Yes and no. If I had to do everything by myself, I would need to write PWM into the code. Also, I could use a normal DC motor and make a driver myself. Servomotors already include a board that processes PWM signal and controls the electric motor inside. And since I'm using Arduino, there is a library for servomotors. It includes 6 functions and 2 examples. Attach and write are the 2 functions that we are going to use. Attach defines which pin is used to control a servomotor. Write is a function defining the position of servo's arm, going from 0 to 180, 90 being in the middle. Now let's take a look at sweep sketch. It rotates the arm between extreme positions, back and forth. Comments explain all of it in detail. I would like to see how fast it can turn, so I made this simple program. It basically sets arm's position to either 0 or 180 and changes between them. Delay is there, so the PWM signal is not sent too early, before it fully rotates. It is pretty quick, still I don't know how accurate it is, so I would like to now check it with physical inputs. I could use the second sketch to see how it works with a potentiometer, but this would be too simple. Instead, I'm going to use 2 push buttons and mount a laser diode on top of it. First, I secured laser board using glue and rubber bands. Then, I built 2 button circuit, power to the buttons from Arduino, left button to pin 4, right button to pin 5. Also, I placed 100 microfarads capacitor between power leads of the servo. Now, decode. First, include servo library. Then, I defined 2 button pins, add position variable, and set it to the middle position. Next, define 2 variables, one for each button. Setup includes serial communication, attaching the servo, and setting button pins as inputs. In the main loop, first I read button values and put them into corresponding variables. Then, if the left button is pressed and the right isn't, position changes by 2 degrees to the left, or the other way around. I could change the value at which position changes, and the servo would go slower or faster. After this, position is sent to the servo. The last part is just to limit the value of position variable. Rest of the code is used to check in serial monitor if everything works as intended. Now only thing left is to see how it operates. I would say that this is a good starting point. If I include a second servomotor in the parallel axis, it will be even better. I also think that variable speed is necessary for better accuracy and smooth operation. But that is a task for the next video. The main thing that I want to do next is to use PS4 controller inputs to move servomotors. To do this, I need to revisit serial communication. The position of one analog stick can be sent to Arduino. I took a peek at values that ESP32 gets from the controller. I could send them to Arduino and then map those values to different speeds. I will try to make a provisional construction that allows to connect two servos and laser board together. I don't have a 3D printer, so tape and glue it is. That is it for this video. I'll get to the more complex stuff in the next one. Links to all components are in the description as Amazon links. If you enjoyed this video, subscribe and leave a like. Do you think that I should include something else in this project? Then leave a comment. And see you in the next one.